Welcome students to our new topic and second part of this course, that is acceptor complexes, or sometimes they are also called pi acceptor ligands, the ligand which participate in this type of chemistry. I'm quite sure that you are familiar with the coordination chemistry of certain compounds, and coordination compounds are those compounds in which the central metal atom is surrounded by a sheath of ligands, and the bond between metal and ligand is predominantly coordinate covalent bond. Also, you are aware of the definition of ligand, that ligand is a species which can be neutral, can be anionic, and can be cationic, which is capable of donating a pair of electron to the metal center. And also the concept of Lewis acid and Lewis base is applicable in coordination chemistry, that metals are Lewis acids and ligands are Lewis bases. So, coming toward the history of acceptor complexes, it was 1884, and Ludwig Mund was working in certain industry. In that industry, they were dealing with carbon monoxide gas, or certain industrial process where carbon monoxide gas was evolved, and this gas was passed through certain exhaust system, and in that exhaust system there were some nickel walls. So they observed that after some time these nickel valves they decay, or they were eaten away. So they were aware that carbon monoxide is produced inside the chemical process, and probably this carbon monoxide is responsible for decay of nickel walls. And after some time, they were compelled to change or replace the nickel walls because of leakage of certain industrial effluents or gases at unwanted places. Now, what Ludwig Mund did, he deliberately heated nickel powder in a stream of carbon monoxide. Whenever we are talking about nickel powder, so nickel powder, definitely it was impure nickel from raw material, and in a stream of carbon monoxide, so means at high temperature carbon monoxide was treated with this nickel powder. What happened? He produced volatile nickel carbonyl complex, and in coordination chemistry this is tetracarbonyl nickel 0. Whenever this nickel carbonyl complex was produced, so this was a real revolution in the nickel refining industry, because Ludwig Mund was also able to dissociate this compound into pure nickel and carbon monoxide. And as you are aware of certain industrial process, then separation of nickel and carbon monoxide was quite easy, because nickel will be obtained as solid and carbon monoxide is a well established gas. So separation of solid from gaseous material, there is no technical issue in their separation. So separation was easy. Nickel was obtained in 100% pure form. Carbon monoxide was re-entered into the process, and because of this revolutionary reaction, or this revolutionary step, what we found, or what the industrial community obtained or got. So the nickel refining is nowadays also based on this experiment, which was conducted by Ludwig Mund in 1884. And in this case, this is the nickel complex, neutral complex, and this neutral complex, by providing certain amount of heat, can be converted into pure nickel. This is general reaction, that whenever nickel was converted into nickel carbonyl, so by providing again certain amount of heat to this complex, nickel and carbon monoxide 4 moles can be obtained, and this carbon monoxide now can enters back into the process and can make certain other more volatile nickel carbonyls, and those nickel carbonyls again will be pass through certain chamber where heat will be provided, and during that heating system, the nickel and carbon monoxide or nickel carbonyl will get dissociate to give nickel and carbon monoxide, and after condensation, the nickel in pure form will be obtained and carbon monoxide will be evolved in the form of a gas. So this is the step, this is the reaction which is also currently used in nickel refinery industry. At that time, there was a scientist whose name was Lord Kelvin, and he was really impressed by this discovery of Mond. And at that time, he issued a statement that Ludwig gave wings to nickel. And this statement, or this reaction, or this step, was a revolutionary step in nickel refinery and refining industry. Now, this was not easy to understand because carbon monoxide is a well established gas, it is very stable, it existed free in nature, and nickel itself in zero oxidation state. This is not easy to understand that why nickel in zero oxidation state reacts, because this is normally inert. So one stable species, when was combined with another stable species, and a third species or compound was formed. So for the chemist of that time, it was not easy to understand that why a neutral metal reacts with a neutral molecule. What is the logic behind it, and how stable the bond will be, what will be the chemistry of the bonding, how electrons will come from metal to ligand or ligand to metal. So this was a real mystery, and now the scientists tried to explain the bonding between carbon monoxide and nickel in the respective complex. Now, carbon monoxide, we believe that there is a bond between carbon and oxygen. The bond is expected to be multiple because carbon is capable of making more than one bond. Oxygen normally makes two bonds, so at least we expect two bonds between carbon and oxygen. And on the basis of this multiple bond, we will also later on discuss the softness and hardness of ligands. But here you should keep in mind that carbon monoxide is a soft ligand, and this soft ligand are the molecule made of carbon and oxygen. This is now a very efficient ligand for metal in oxidation state zero. So this is another chemistry that are another concept that what are soft ligands. So soft ligands are those ligands which are capable of stabilizing metal in their low oxidation state or zero oxidation state. So nickel in the complex, nickel in free state, and nickel in raw material or raw state, it is in zero oxidation state, and there is no change in oxidation state of nickel throughout the process, from raw material to 100% pure nickel, and from free nickel on both the sides of the process to the compound of the nickel, where in each case the nickel is in zero oxidation state. And by nomenclature, this is tetracarbonyl nickel zero. So again, we have to mention the oxidation state of nickel in the name of the complex during naming it as according to IUPAC system. Now, let going a little bit more forward. So this metal, which is ligand, this is capable of accepting pi electrons from the ligand. It is accepting ligand electrons from ligand with the help of sigma bond, and the metal itself, it is electron rich because nickel in zero oxidation state, it possesses 10 electron in its valence shell. And if you draw electronic configuration of nickel, so this is D10 D8 system. So D8 means d orbital subshell is rich in electrons, and now there are chances that nickel is also, or nickel probably would be able to donate some electrons to the ligand back. So sigma bond, that is known in general chemistry, that whenever two or more than two species combine with each other, they establish a bond, and normally that bond which is single, that is called sigma bond. So in sigma bond we will also come to the so we are coming to the bonding situation of carbon monoxide and nickel in later slides. But in this case, just keep it in mind that d pi and p pi, we will use these two terms, or these two symbols, or what we can say concepts, in bonding between nickel and carbon monoxide. So the nickel is capable to accept electrons from the ligand in d orbital, and it donates back electrons to the ligand again from d orbital. So we will also come toward hybridization, that what type of hybridization would be there. So the ligand is sigma donor because the bond between metal and the carbon monoxide, which is formed as a result of normal or conventional electron donation from ligand to metal. So that will be sigma bond. And the bond which is formed between metal and ligand by back bonding or back donation from metal to ligand, that is not a normal phenomena. So that type of bond is called back bonding. And this, on the basis of this back bonding, where the electron will be accepted in the ligand. So now we will come also to the orbital, that which orbitals are involved in sigma bonding and which type of orbitals are involved in pi bonding. So because carbon monoxide accepts electron in its pi orbital, so therefore the carbonyl are called pi acceptor ligands too. So they are sigma donor and pi acceptors, and on the metal side, only d orbital is will be involved in bonding, or in sigma bond maybe some type of or some sort of hybridized orbital or s orbital can also get involved. So now let's come to the electronic configuration of carbon. So this is electronic configuration of carbon, where two electrons are in ultimate shell or outermost subshell, that is 2p, 1s and 2s are filled. Of considering the electronic configuration of oxygen, we have to place electron in their respective orbitals. So it has 4 electrons in p orbital. Now placing these orbitals, these electrons in their respective orbitals, so 1s is filled, 2s is filled, and there are 2 electrons in p with same spin or spin paired electrons they are. And for oxygen, now two orbitals where they are 1s and 2s, they are filled. There is a pair of electrons in p and 2 electrons are unpaired. Now how they will get involved in bonding? Now according to valence bond theory, we have to apply that concept. So according to this theory, what we have to do in normal compounds, they share their unpaired electrons. So as per our concept, what we have to do, the oxygen and carbon will share their unpaired electrons. So carbon has unpaired electrons which are 2 in numbers, oxygen has unpaired electrons which are 2 in numbers. So there are chances for these electrons to get paired up, and because of pairing they will afford certain bonding. So again, let represent the electrons of carbon in a little bit modified form, and electrons of oxygen in a little bit modified form. So s orbitals are out of the bonding because they do not participate in bonding, and because of the reason that they are filled, and filled orbitals are there to do nothing with the bonding between two species. So now the chance is only these unpaired electrons will share. The atoms carbon and oxygen will share these unpaired electrons with each other, and since they are one in each orbit, so resultantly two pairs will be obtained. Now this is electronic structure or atomic structure of carbon and oxygen. So in carbon and oxygen, let's put electrons of valence shell, which is 2s and 2p. So 2s electrons in carbon are here, and this s orbital is not involved in bonding. Similarly, 2s electrons of oxygen are here. The subshell is not involved in bonding. two electrons which have been shared between carbon and oxygen, or they have been mutually shared. So these two electrons from oxygen, which I have marked as red, and green are electrons of carbon. So there are four electrons now which are shared by both carbon and oxygen. And